All right, and we are back with another lecture of Design and Analysis of Experiments, Stat 568. And today we're going to be continuing our look at the full factorial design and going a little bit deeper into its study. So in today's lecture, what we're going to do is we're going to be looking at the full factorial design and specifically blocking for the full factorial design, because when we have so many factors and so many interactions and we're running out of degrees of freedom, where are we going to put the block factors? And that is going to be a challenge. It's going to involve a little bit of group theory. It's pretty fun. So let's go check that out.
And welcome to another lecture of Statistics 568, Design and Analysis of Experiments. Today we're going to continue our discussion on the full factorial design and talk about a couple special topics that go along with it. So when we first looked at the full factorial design last time, we set up the entire idea. We said that we have k factors, each are binary valued, so 2 levels each. It's going to lead us to a sample size of 2 to the k. That may be pretty big, so big that we may not want to replicate it. And there's going to be a lot of interaction effects to consider, from the main effects to the 2-way, 3-way, 4-way, up to k-way interactions. We looked at things like Lentz method, which is a way of computing p-values for the significance of each of the main and interaction effects when we don't have enough degrees of freedoms for the residuals to actually run an f-test. And now what we're going to do is we're going to continue on to and sort of tidy up some various concepts, talk about some rules of thumb, talk about testing for homogeneous variances, and talk about blocking for full factorial design. So let's get into that. When we're doing testing for full factorial designs, there's a couple concepts that we should keep in mind, or I'll say rules in quotes, because they're meant to be broken, but rules to keep in mind. And the idea is that for a 2 to the k design, we have 2 to the k minus 1 different main and interactions, interaction effects to test. So when we're doing this, well, what do we expect to see, right? In some sense, we could see anything, because I could simulate crazy data that can give me all sorts of strange results. But in practice, when working in the real world, there are some things that we would expect to see. The first is this notion of hierarchy. Hierarchy. Right. And the idea here is that lower order effects are often more significant than higher order effects, that is, interactions. I'll say lower order interactions are usually, not always, usually more significant than higher order interactions, with main effects being considered a first order interaction, I guess, or being more likely to be significant than anything else. So does it mean that a high order interaction can't be significant? No, it doesn't mean that. But what it means is that on average, when we're running an experiment, we would expect that factor A or maybe factor B would be significant, or the interaction between A and B. But we're less likely to see something like an interaction between A and B and G and F and K and whatever, all interacting in some way. You could imagine this if this is a cocktail of drugs that people are taking. Okay, maybe there are going to be some interactions, but the odds that like 10 of them are all going to be somehow significantly interacting together is quite low. It could happen, but it probably won't. Again, that's why it's our rule to keep in mind. The second concept is that of sparsity. Most of the 2 to the k minus 1 effects, main and interaction effects, are not significant. Again, this may be violated, maybe everything is really significant, but in general, we have a lot of different main and a lot of different interaction effects to consider. In practice, you probably won't see a lot of them being significant. There will just be a few. So it's more like the needle in the haystack problem. I have 2 to the k or 2 to the k minus 1 different things I'm estimating, and I need to find out which ones are significant. There's probably only a couple that will be significant. Again, not a law of the universe, but something that we generally see in practice when working with data. The last one is heredity. And this is usually an interaction is significant only if one of its pieces, for lack of a better word, is significant. One or more, I should say, but the idea is that if we have a significant interaction between factors A, B, and C, we'd probably expect at least one of those to be significant on their own. So that's the idea of heredity, is that you would expect some type of a tree-like structure, I guess, where A is significant and maybe B is significant, and then A crossed with B is also significant, and something like that. Now, again, it doesn't have to happen that way. You might have two compounds that are inert, but when you ingest them both at the same time, then suddenly you have an effect, a significant effect. So you never know what's going to happen in practice. This is just what we typically see when looking at lots of studies and lots of data sets. You know, if you have a fertilizer that helps the plants grow and you have a pesticide that helps the plants grow, then when you combine them and get an interaction, yeah, it's probably going to, maybe there's a reinforcing effect there, or maybe they cancel out each other, like the pesticide somehow degrades the fertilizer and they don't have the same additive effect they would have if they weren't interacting. But again, typically you wouldn't have two things that just are null, not interesting at all. But then when you put them together, suddenly it's a significant effect. So again, it can happen. It probably won't, but it could. So always be on the lookout and try to, stay on your toes when you're analyzing data. Anyway, those are just some rules to be aware of. It's going to come back again when we consider topics like blocking and fractional designs, because when we do blocking, when we do fractional designs, we can't test all 2 to the k minus 1 different effects, and we have to choose, well, which one should we test? And typically we can use the ideas of hierarchy and heredity to say, let's just get rid of the big terms, the big interactions, because the odds that those big interactions are going to be in any way interesting are pretty low. So if we have to throw something out of our model, throw away the big terms, keep the small terms, that is the main effects and the second order and maybe the third order or whatever. But yeah, so that's roughly why it's good to talk about these things. And similar with sparsity, because this is going to come into the idea of multiple testing correction, right? Remember when we looked at multiple testing correction in the previous chapter, I guess 2 lectures and 3 lectures ago? Typically, you're correcting the multiple testing methods typically work better if most of the p-values are null or not interesting, because there's that I naught term that we were sort of just rounding up to m, the total sample size, or total number of tests. Well, the idea is that if most of the tests are producing uninteresting, not significant p-values, that actually kind of helps the multiple testing methods find those few that really are significant. So ideally, it would be a good setting for multiple testing correction if we dare use it. Some authors actually say don't even bother, because just report sums of squares and don't even worry about multiple testing correction, because it's just going to make you miss something that you otherwise should have caught. So, again, it's all kind of an art to the statistics, right? There's no hard, strict rules as to how to analyze data sets and what methods to use. But if you are going to use something like an F-test, you want to make sure that your variances are homogeneous, because that's one of the big assumptions that we have here when we're studying design of experiments, with the assumption of normality and with the assumption of homogeneous variances. So the next little section we're going to talk about is a little bit of a diversion from the factorial design, but it's a good place to talk about it, which is dispersion and variance, homogeneity. And we talked about this already. We talked about this by looking at Bartlett's test. I didn't tell you what Bartlett's test does, or I didn't tell you what it is. I just told you what it does. What it does is it tests to say, are the variances the same among different categories? So I have a single factor that's going to break up my data set into however many categories based on the number of levels. And I want to know, are the variances all about the same up to some statistical testing, or are they different? So how do we do that? Well, basically, if we have a 2 to the k design, and I guess in this case we're assuming that we replicate n times, then we can compute sample variances for each of the treatments, that is, for every row. Then every treatment, remember the treatment is a row, it's a combination of factor levels, can have a sample variance. Now, okay, what you could also do, right, is you could take an individual factor that just splits your data set in half, and you could run a test for variance homogeneity on that. And there we just take half the data set, the other half, and look and say, well, is the variance of this half about the same as the variance of that half? The way I have it phrased here is that if we technically would want to look at every single treatment. Now, if we don't replicate, we only have one observation of every treatment, we can't test for variance with one observation. There's no estimate for the variance there. But if we replicate this design more than once, we'll have at least 2, or in this case, n observations per treatment per row. And as a result, we can use that to then compute a sample variance for each treatment. And we might want to know, well, do all the treatments have the same kind of variance or not? So yeah, that's just a subtle point, but that's why I'm writing it this way. Anyway, what we can do is we can write down the sample variance, nothing too profound. It probably shows up in Stats 101 when you take that. But effectively, I'm going to sum up everything in the jth. I'm going to sum over j of the observations yij, and I'm going to get y bar I dot here squared. So that's it. Basically, what we have here is the ith treatment, the jth observation in that treatment, and this is the treatment average, ith treatment average. All right. Okay, so that's fine, not that interesting, but we can actually go a little bit further, because assuming normality in the errors, reasonable enough assumption. If we assume the errors have a normal distribution, then what does it mean when we what does it mean for our SI squared here? Well, it means that our SI squared is going to look like a chi-squared distribution, because if you take a normal random variable and you square it, you're going to get something that looks chi-squared. Now, what I really mean is you take something normal, you subtract the mean, you normalize it, normalize the normal, divide by the standard deviation to get a variance of 1, and then you square it, and then you get a chi-squared random variable. In our case, what we get is that n minus 1 times s squared I divided by sigma squared, which is the variance of the errors. This thing will have a chi-squared distribution with n minus 1 degrees of freedom. Right? It's just a sum of a bunch of centered normal random variables, and then we scale it by n minus 1 and sigma squared. Yeah. Okay, so what do we do with that? Well, what we ultimately are trying to do is we're going to try to come up with a test statistic for testing for variance homogeneity, and we're going to use the fact that we have a bunch of scaled chi-squared random variables here. So these guys, the S's, are all scaled chi-squared random variables. How do we come up with a test statistic for that? Well, basically, to get a test statistic for, it's always good to write down your hypothesis test. I should do that first, which is that sigma squared. Do I want sigma squared here? Sigma squared, I actually don't want. That's the... I'm trying to figure out what the right notation is, because technically sigma squared is the variance. What I'll say is sigma 1, because sigma squared would be our homogeneous sort of error variance. But what we're assuming is that the variance for each of the categories from, it's not going to be up to n, it's going to be up to, we'll just say m, if there are m different treatments. So our null hypothesis is that all of the variances are the same. Our alternative is that, using the math jargon lingo, there exists a j such that sigma, or let's say I and j, such that sigma I squared is not equal to sigma j squared. So at least two of the categories have different variances. So that's what we want to test. How do we do that? Well, first, we define x squared, and x squared is going to be x squared sub I, and x squared sub I is going to be a random variable. It's going to be si squared divided by sigma squared. It's the same thing as I had kind of up here, just without that n minus 1. Okay, and what we're actually going to be interested in is the log of this. But first, we note that the expected value of xi squared, the mean, is going to be what? Well, the si squared is an unbiased estimator for, I should put sigma I, but I guess we're assuming we're in the null hypothesis case, so it's always going to just be sigma. That's where I was confusing myself earlier, right? In the null hypothesis case, all of the sigmas are equal to each other, so we don't need a subscript. In the alternative, they would be different. But in this case, our SIs should all be estimators, unbiased estimators for sigma squared. So what I end up with is something that looks like sigma squared divided by sigma squared, which is just 1. So it has a mean of 1, and its variance, xi squared, is going to be what? Well, what's the variance of a chi-squared distribution? It's 2 times its degrees of freedom. So in this case, we're going to get 2 times the degrees of freedom but we're actually, in some sense, dividing by n minus 1, and it comes as an n minus 1 squared. And we're left with 2 divided by n minus 1. Let's change the color scheme for my boxes here. And we have the mean and the variance. So that's nice. The reason it's nice is because sigma squared is not in any of my green boxes, right? So this is what you do when you want to test something in statistics. You want to try to get rid of all the parameters that you don't know what they are, because you can't do anything if you have a parameter that you don't know what it is. Instead, we want to get something like, well, 1, that's a good number. I know what 1 is, and I know what 2 divided by n minus 1 is, because n is the number of replicates, or the number of observations per treatment category. And we're assuming, again, it's the same for all of them. If it's not, you can kind of adapt this, but it's super annoying to write that all out. So we're going to assume that we have the same number of observations per category to make our lives a lot easier. Okay, so now that we have this, the question is, well, how do we construct a statistical test? Now, the way that they talk about it in the textbooks is to say, consider the log of xi squared. Okay, so what happens when you have a scaled chi-squared random variable and you take a log of it? Well, what happens is that this thing, well, let's get down to the, where is the conclusion? Okay, well, we'll just go through it step by step because I forget what the exact answer is. So we'll just work through it. And what we find is that the expected value of the log of xi squared is approximately 0. So that's not unreasonable, because if the expected value of, like intuitively, if the expected value of xi squared is equal to 1, then if I take the log of 1, I get 0. But that's not how expectations work. So we have to be a little careful. In fact, I'll say more precisely, what we have is that the expected value of the log of xi squared is going to be less than or equal to the log of the expected value of xi squared, which is the log of 1, which is 0. This inequality comes from one of my favorite tools in statistics and probability theory. It's Jensen's inequality, based on the fact that, I guess, log is a concave function, not a convex, concave function. You can take it out of the expectation. So actually, it turns out that this expected value is less than or equal to 0, not approximately 0. But we can actually go a little bit further and use something called the delta method to figure out what's going on here. So the delta method says that if, let's see, where are we here? Yeah, so what do we know about a chi-squared random variable? We know that a chi-squared random variable, as the degrees of freedom goes to infinity, starts to look like a normal distribution. There's a central limit theorem going on here. So what that means is that if we have xi squared, and we subtract its mean, and we scale this by, I guess, n. Yeah, I guess I just have to scale this by the square root of the sample size. Let me double check that. Yeah, square root, it's always the square root of the sample size. So if I have something like this, and I know that in distribution, what I have is a scaled chi-squared, it's a centered, and it's, well, xi squared is a scaled chi-squared random variable. If I center it, then what I'm going to get is a convergence to a normal distribution with mean 0, because I subtracted the mean, and the variance is going to be what's in my blue box up there. So this is still the if part. It's not the then part. The if part just says this, says that if we have this condition, and this is true via the central limit theorem, CLT. So because of the central limit theorem, we have that our xi squared converges to a normal in distribution. It's interesting. It makes me wonder why they don't just use the xi squared itself, or they don't use that for the test statistic. Well, I guess it still has sigma squared in it, so you can't do that. Okay, yeah, that was a silly point. Of course you can't do that. But anyway, the delta method says that if we have a central limit-like theorem for x squared, then we're going to have one for a function of x squared. So we say then what we get is that root n log of xi squared minus the, I think it's the log of 1, which is just 0, but we'll just do that anyway, is going to converge in distribution to something normal that is still mean 0, but now the variance, okay, the variance is supposed to change, but in this case it doesn't. What you get is you get the old variance, and then you have to multiply by the derivative of, we'll say t, of log t. This thing evaluated, I guess this thing evaluated at 1, the expected value, and then this whole thing is squared. But luckily, that's just going to be 1. So it's a terrible, terrible thing to write down here. But this guy is actually just going to be normal 0, 2 over n minus 1. So the neat thing is that we took a log transform, and it turns out that the mean and variance are invariant to the transform. They stay the same. So that's kind of neat, because you'd think off the top of your head, you think, well, if I take a log transform, that should probably change things, right? Well, in this case, I guess it does one thing. It changes the mean. The mean goes from 1 to 0, but the variance stays the same. Anyway, so why are we doing that? Well, we do that because, therefore, the log of si squared, that's the thing we care about, is going to be the log of xi squared minus the log of sigma squared. Okay, we just took our ratio and we applied a log to it. So that's, oh, sorry, this is a plus. So therefore, what that means is that the log of si squared is going to be it's going to be distributed. Well, it's not distributed. It's, we'll say, converges in distribution to a normal random variable with log sigma squared as the mean and a variance 2 over n minus 1, which luckily has nothing to do with sigma squared. So now what we have is we have a normal distribution. The mean is in terms of sigma squared. The variance is just the variance, has nothing to do with sigma squared. And that's great because we can use that to now do a statistical test. All right, so given that we have a normal distribution now for the log of, well, si squared, that is asymptotic normal distribution, we can use that to construct a hypothesis test, or a test statistic to be used for a hypothesis test. Now, how do we go about doing that? Well, there's different approaches. There's the approach that I found in Wu and Hamada, the textbook on design of experiment. And what they say is okay, let's define two things. We're going to define Zi to be the log of Si squared, and we're going to define Z bar to be a, well, weighted sample mean. In our case, I'm assuming that every category has the same number of observations, but just to be as general as possible, what we can do is we can write this down and this sample mean down in this form. which is going to look like ni minus 1 zi, and I should probably say where capital N is the sum I from 1 to n of little m, I from 1 to m of little ni. But in our case, I'm assuming that all of the categories have the same number of observations to make things easier, which is just going to be little n times little m. So in our case, this is just going to be nm. But that's all that this is doing. It's just basically saying scale the, have a mean where we weight each observation based on how much data is giving us that observation. If one category has tons of data, we give it a higher weight. If another category has only a little bit of data, we don't give it as significant of a weight. Significant is kind of a loaded term in stat, so I probably shouldn't say significant, as large of a weight. Anyway, then what they claim is that if I look at the sum, I from 1 to m, remember m is the total number of treatments or categories that we're testing over, and I have my, first something, we scale this by the sample, the individual sample size ni minus 1 over 2 divided by 2, and then we take our zi minus z bar squared, and the claim is that this converges in distribution to a chi-squared random variable with m minus 1 degrees of freedom. So is that reasonable? Well, yeah, because what we're doing here is we're taking the zi, which is really just the log of the si, right? It's just a more convenient way to write. This is zi here. It's normal. If I subtract off the mean and I square it, then I'm going to get something that's going to look like a chi-squared, except that we have to adjust for the variance not being equal to 1. And we do that by multiplying by this thing here. So basically what we're doing is we're summing up a bunch of normal 0, 1 random variables squared with the one lost degree of freedom for the fact that we are estimating the sample mean, as we don't have the true mean. And that's where we lose our 1 degree of freedom. So otherwise, we're just taking a normal distribution and we're constructing a chi-squared test statistic from it. Now, that's not Bartlett's test. Bartlett's test is, kind of the same idea, but it's going to look a little bit different. We have Bartlett's test. So Bartlett's test statistic is going to look like this, using the general notation for unequal sample sizes. It's going to look like the log of S bar, which is the average. S bar squared is the average of the sample variances, so slightly different than Z bar. Z bar is the average of the logs, whereas this is the log of the average, right? Anyway, we have that, and then we're going to subtract off the sum I from 1 to m of ni minus 1 log si squared, and we're going to divide that thing by some crazy term, which is going to look like this. So where this came from, it's ultimately trying to do the same thing as that simpler test statistic above is doing. What you're doing is you are effectively taking your normal distribution, you're squaring stuff, you're normalizing in the denominator by some crazy term that I'm not going to try to actually derive myself, because I really don't want to. And you end up with something that looks like this. Why is there a 3 in the denominator term? I have no idea. But ultimately, the reason for all of these terms is to, again, take your test statistic, I guess, or you take your take your sample variances or the log of the sample variances, center them by a mean, divide by some type of variance term to normalize it, and what you should get is convergence in distribution to a chi-squared random variable with m-1 degrees of freedom yet again. So we actually get the exact same asymptotic distribution as the other test statistic here. But there are differences. And then the question is, well, which one do we actually use in practice? Well, Bartlett's test is coded up in R under bartlett.test, so that makes it really easy to use. Of course, you could try using this other method too. I don't know if it exists in R, but it would be very simple to code on your own. Now, there actually are even other tests for the homogeneity of variance, and there's really no, I don't know of any really strong reason to choose one over the other. What you would need to do if you really wanted to know which one was better is do some type of a survey simulation study where you could test a lot of randomly generated data, some simulated data, and see which one gives you the best statistical power for rejecting the null hypothesis. That is, which is the best at determining when the variances are different. Because ultimately, as the data size gets large, or the number of tests in this case, I guess, gets large, they're both going to be converging in on the exact same thing, which is a chi-square distribution. But remember, they don't have a chi-square distribution. They have a chi-square distribution asymptotically. And if we're not in the asymptotic world, also known as asymptopia, we don't have a chi-square distribution. We have something that's going to be getting close to it. Therefore, we're not going to have a perfect statistical test. It's really just asymptotically correct. Hence, if you really want to know, you can try and test it yourself, or you can just use Bartlett's test because it's there and it's coded and it's easy and you don't have to think about it. So, yep, there's my rant on statistical testing and asymptotic tests. I've always been a fan of non-asymptotic tests, but that's a discussion for another day. Anyway, we're moving on to the next section, which is blocking with factorial design. So this is the last thing we're going to do before we jump into the dreaded fractional factorial designs and things start to get kind of crazy. But what we need to do is we need to figure out, well, how are we going to add blocking factors to our factorial design? Now, the reason why I say how are we going to do that is because if we have an unreplicated factorial design, we now have, again, 2 to the k different observations. We have 2 to the k minus 1 different main and interaction effects that we will be testing. And we've used up every degree of freedom we have. So where do we put the block factor? We put the block factor on top of one of the other treatment factors, and this confounds it. So that's what we're going to look at. So basically, there is no more room for additional factors in a 2 to the k design. Therefore, our block factor will overlap one that overlap what is one, overlap a factor, and not a factor, overlap a main, well, not a main, we never want to overlap a main effect. Overlap, we'll just say overlap an effect. So it's going to overlap something else. That could be an interaction effect. It could be a main effect. We typically don't want it to overlap any main effects because, again, assuming that hierarchy principle, the main effects are the most important things to test. All of those high order interactions, probably not interesting. So we can overlap one of those with a block factor. And this is called confounding. And that's what we have to worry about. How do we confound, but properly confound one of our interaction effects in our model with a block factor? So let's do an example. Let's see if we okay, so let's do an example. And maybe the example is we have a medical trial, because why not? Let's say we have a 2 to the 3 design with 3 different drugs to take. Maybe it's a blood pressure medication, because that's the default one I always go to. So let's say we have 3 different types of drugs that may or may not affect one's blood pressure. And what we do is we want to test everything. Actually, you know what we're going to do? At the risk of destroying my recording, I am going to go find this and copy it over from my notes. So, all right, so I have my 2 to the 3 design now, which also includes not just the settings for the treatments, but it has all of the interactions. Remember, we talked about in the last lecture that I can combine my treatments to get interaction terms. And what I'm really doing is an XOR operation. If the treatments have the same value, here I use dot instead of minus because it makes the table a little bit easier to look at. So if I have a dot and a dot for 1 and 2, then the interaction says it's a plus because it's, again, like an XOR operation. They agree, so they get a plus. If 1 and 2 disagree, they get a dot or a minus sign. So this is what our entire table looks like with the 3 treatments, 1, 2, and 3, and the interactions 1, 2, 1, 3, 2, 3, and the 3-way interaction 1, 2, 3. So what we can imagine is that each of these is going to be 1, 2, and 3 would correspond to, say, taking some type of a drug to see how it affects your blood pressure, say. But maybe we want to block by old versus young. So we pick a threshold, whatever the definition of being old is. I'm not going to specify one in a recorded video, but you can pick whatever your threshold is, and you can find people in the old category and people in the young category, and then test them. But then the question is, well, how in the world do we split up our 8 subjects, right? Because what I effectively want to do is I want to, say, take maybe the first 4 and call these the old ones, and then take the next 4 and call these the young ones. So that might make sense. But if we consider this to be a binary factor, then what I'm getting is a dot, 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 and a plus, 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 plus. And this is the same as column 1. So in this case, we just confounded, I guess, factor 1, drug 1. And that's bad because that means that if we found a significant difference in the blood pressures for that column, we don't know if it's coming from drug 1 or if it's coming from the fact that old people and young people may on average have different blood pressures, right? So we don't want to do that. That's bad. Just to emphasize, if it's not clear, we don't want to do that. That's bad because now we can no longer test for the significance of, I guess, treatment 1 or factor 1. So instead, we have to pick a different column. Now, what you might be saying is, well, wait, what if I just did something like this? What if I switched to these 2? So instead of that, I had a plus and a minus. Well, now we have another problem. I should probably keep this the same for the note, but if we do this, now we have a new problem. And this problem is we are not balanced. Because remember, what we really want is we want everything to be balanced. Being balanced means that we have the basically each of the treatments and factors is considered an equal number of time within each block. And in this case, treatment number 1 would occur in block. Let me switch this to a dot just to. Basically, in this case, we would have 3 occurrences of treatment of the minus level for 1 in this block and 1 occurrence of the plus level. So what I'm saying is we would have something that looks like this. So this is not a balanced block, because in one of the block levels we see more of, let's say, the treatment 1 at the minus level, and in the other block we see more of treatment 1 at the plus level, and that's a problem because it's not balanced. So basically what we need to do is to have a balanced block, we must pick one of those columns. Okay, so what we really need to do is let's see if I can, good, I got it again. So really what we need to do is we need to take this and decide which column do we want to confound, which would be the most reasonable one to basically destroy. And in this case, the answer is, unless it's a very strange testing scenario, the answer is we want to confound the highest order term. So what we would do is our block term would look like this, which basically means now if we get significance in that, these two are now confounded. They are effectively the same thing. If we see significance there, we don't know if it's the block or if it's a 3-way interaction term. We chose the 3-way interaction term because we assume that of all of the 7 different things I'm trying to test here, the 3-way term is probably going to be the one that is least likely to be significant. As I mentioned earlier when we talked about the idea of hierarchy in factorial designs. So that's the idea of confounding. But it gets a little bit more complicated when we want another block. So let's say, I'll say, but what if we want another block? What if we have 2 blocks? So if we had the age variable and say a sex variable, so we want to know if men and women have different blood pressures on average, right? We might want to cut our data set in half again with another block. So, well, we have to pick another column. The answer, pick another column. Okay, so what would be another good column to pick? Well, we have 3 2-way interactions, so let's just pick one of them and see what happens. Okay, so I'm going to pick this as, so now we have, this will be block 2. But wait a minute, there's another issue here. If I confound 2 columns, I'm actually also confounding the product or the XOR of those 2 columns. So what happens when I combine 2 and 3 and 1, 2, and 3? What I end up with is I actually have also confounded this column. Main effect 1. And that's bad. I'm already in red, so we'll use blue to say bad. right? Ideally, we would never want to confound a main effect, because if we're confounding a main effect, we shouldn't even include it in the first place, because you're basically like, I'm going to test this drug, and then I'm going to destroy my ability to test this drug. Yeah, it doesn't make any sense. But the point is that you could be very, eloquently trying to block away, confound the higher order terms, but you did something wrong, and then suddenly you lose the ability to test a lower order term or a main effect, and that can get you into trouble. So why in the world does confounding these two higher terms, the 1, 2, 3 and the 2, 3, also confound 1? Well, if we stare at the table, we'll notice that in the first 4 observations, the plus and the 2 columns always differ from each other. In the latter 4 observations, they're always the same. So what's happening here is that if we were to, again, do an XOR operation, we end up with column 1. So what we end up with is something like this. If we say 2, 3, and I'll use this notation, plus 1, 2, 3, well, it turns out we get 1. Now, this is why I'm trying to write the notation like this, because it turns out that we can actually generalize this. This is what we call a group in mathematics. It's, in fact, I think an abelian group, right? Because it should be commutative, right? Yeah, so it should be finite. Yeah, finite abelian group is the right term. So, fun math fact. We have a finite abelian group. Abelian. Is it abelian or abelian? I'm going to double check that. No, I have it spelled wrong. It's not abelian, it's abelian, because it's after Abel, right? Or Abel. Okay. There's no L in there. All right, so we're back. We're going to do a little bit of group theory. I bet you didn't see that one coming when you signed up for this course. What we're going to do is consider columns 1, 2, and 3. So here, I'll say T for, we'll say F for factor. I feel like I should say factor and not treatment. We'll say factor 1. And that is going to look like a vector of, we'll say -1, -1, -1, -1, +1, +1, +1, +1. Now, this vector is quite interesting because if I, multiply it by itself, or if I multiply itself entry-wise, so if we say F1, I don't have a mathematical notation for this, so I'm just going to write star. Because we're not doing a vector, you can't multiply 2 vectors, but you can do an entry-wise multiplication. If I multiply it entry-wise, I get 1, 1, 1, 1, 1, 1, 1, 1. Okay. So what I actually have here is that F1 has order 2, i.e., if I take F1 and I square it, where all the multiplications are being done entry-wise now, then I just get the identity, which I'm going to write as I, capital I, for identity. Okay. And if we look at this mathematically, what we actually have is a cyclic group of order 2. So this is a cyclic group of order 2. And we can write that, if you have ever taken a group theory course, as Z divided by 2Z. Not a really important point, but that's supposed to be a 2. where Z is the integers. So it's the integers mod 2. It's basically, because I could be doing this all with zeros and ones and XOR operations, but it seemed like multiplication is maybe an easier way to think about it. Anyway, if I have, let's say F1, F2, and F3, what I can do is we can generate a group from these three elements. Now remember, they're all their own inverse. That's the nice thing about them having order 2, which means that if I square them, I get the identity. And what it means here is that I can consider a group, and the group elements are going to be I, F1, the generators, F1, F2, and F3, and then all the pairwise products, F1, F2, F1, F3, F2, F3, and the triple product, F1, F2, F3. And they are, so if you've never taken group theory, groups are just these general mathematical objects. We're in finite group theory now, so forget about everything else. You have elements, and you can multiply them together. This is an abelian group, which means I have commutative multiplication. It's not like matrices where you can't commute and everything gets worse. Here I can multiply, basically F2 times F1 is the same as F1 times F2. And in group theory, we need inverses. Luckily, in this case, each element is its own multiplicative inverse. Which means, as I kind of pointed out up here, if you multiply an element by itself, you get back to the identity. So now that we kind of have that established, the point is that I can rewrite this and drop the F's, because the F's are just going to be annoying. I'm going to have I as my identity, and then I can have 1, 2, 3. Well, I'll just forget the parentheses. We'll just say 1, 2, 1, 3, 2, 3, and 1, 2, 3. So these are all the possible elements I have. These are all the columns. The I actually, statistically, is kind of like the global mean intercept term. It gets thrown out because it's just looking at the average, right? I is in some sense looking at the average over all my data set, whereas all of these other columns, 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3, those are all going to look at different ways to cut my data in half based on this table up here. Now, getting back to this idea of blocking, if I block with one element, so the idea is that blocking creates a subgroup that overlaps with elements, columns of our, I guess, original group of this thing. So what does that mean? Well, that means that, again, if I choose a block factor B1 to be, say, 1, 2, and I choose a block factor B2 to be 1, 3, then these two things generate a confounding subgroup. And the way we find out what's in that is that, well, for a group, we always have the identity that's just there. We're going to have B1, we're going to have B2, and we're going to have the product of B1 and B2. And what does that happen to be? Well, that happens to be I, 1, 2, 1, 3, and the product of those, which is 1 times 2 times 1 times 3, and the ones cancel out, because remember, what you basically have here is something that's going to be, well, the answer is 2, 3, and I'll explain kind of where that comes from. In this case, what we're doing is we're doing 1 times 2, 1 times 3, which, because we can commute multiplication, we get a 1 squared times 2 times 3, which is just the identity, times 2 times 3, which is just 2 times 3. So the easy thing to do is just to kind of look at what numbers are being multiplied together and then start canceling out to figure out what you have here. But it makes things quite complicated because, as we saw before I went on this crazy diversion, if you start by trying to block the largest factors, 1, 2, 3, and 2, 3, you just destroyed a main effect, and that's bad. 1 has entered into your confounding subgroup, and we don't want that. So instead, if we were to pick 1, 2, and 1, 3, we also lose 2, 3 confounded within this, I guess, block, within these block factors. All right, hopefully that kind of makes sense. It might take a little bit of getting used to, and it's going to get worse. So hopefully, if you have questions about that, please ask me. Because now, one thing we need to talk about before we end, oh yeah, we definitely have a lot of material for today's lecture. So what we also need to do is talk about the idea of aberration, or specifically, we want basically, how do we pick blocks for our design? And the answer is that we choose a minimal aberration design. Is there 2 B's or 1? Oh, 1 B. Good. Aberration design. Okay, then the question is, well, what in the world is a minimal aberration design? To determine that, to figure out what that is, we first need to talk about what aberration is. So what we can have is, let's say, given 2 different blocking schemes, or given 2 different sets of blocks, which we can define as, let's say, B1, which is going to be a collection of M blocks, B11 to B1M. And then we'll have capital B2, which will be our other block, B2, 1, 2, up to BM2. We'll do an example after we're done with all this, so stick with me while we go through this. Right, so now what we have is we have 2 different block schemes. These are all indices, the 1 and the 2 superscripts and subscripts, so we're not multiplying or squaring anything here, just to be clear. Then we define a function, which is going to be, in the notation of my notes in the textbook, psi, which is going to map blocking schemes and integers 1 to k into z. So that looks quite nasty, but basically what it says is, given a block set and an interaction order, tell me the output, which is how many factors, effects, maybe I should say, how many effects of that order are confounded. Right? That's what it's going to tell us. It's just an abstract function. But the reason why we write it down is that then we can say, we can define mathematically a minimal aberration design. So the idea is that B2 is said to have less aberration than B1 if, now I got to make sure I use English correctly to make sure I get this right. So let's take a second. If for the smallest I such that psi B1 I is not equal to psi B2 I, then we have that psi B1 I is greater than psi B2 I. Okay, so what is that telling us? What that's saying is that we would want to find the smallest order of interaction where the number of confounded factors between blocks 1 and block 2 differ. And then if block 2 confounds fewer of those interactions, we say that it has less aberration than the block 1. And the minimal aberration design would be any design that minimizes the aberration. So if you have a minimal aberration design, it will always have the same or less aberration than any other design with the same number of blocks in it. Let's do a quick example. So going back to the example that I had above, let's say we have our 2 to the, not k, our 2 to the 3 design with, we'll say B1 is going to contain the blocks 1, which one did I know? B1 was the, let's say it's 1, 2, 3, and 2, 3. And therefore, we also lose the product of those two, which is 1. Even though the 1 is kind of an extra add-on. We don't need to, it's generated by the other two, so we don't need to strictly write it in. But just to be clear, I will write it in. And then in the other case, we had a 1, 2, a 1, 3, and a 2, 3. So what aberration says is we start with, let's say, phi for block 1, for B1 at order 1. And what we say is that here, block 1 confounds a single main effect. So we put a 1 there. When we go to order 2, we find that block 1 confounds a single interaction effect, or two-way interaction effect. And when we go to order 3, we find that we also confound one single order 3 interaction effect. So this is the, I guess, the aberration function for block 1. Now in contrast, we can consider the same thing, but for block 2. For block 2, at order 1, we get a 0. We don't confound any main effects. Then, when we get to order 2, it turns out that we confound 3. All of the order 2 effects have been confounded, but we still have the ability to test our order 3 effect because it was not confounded. So the idea is that we have 2 different ways of putting blocks into our 2 to the 3 factorial design. One is going to give me a value of 1, 1, and 1. The other is going to give me a 0, a 3, and a 0. So if we go back to this sort of abstract notion of which one has less aberration, we would find the smallest index I where they differ. That happens to be when I is equal to 1. And then we say which number is smaller, 1 or 0. 0 is smaller. Therefore, we have that B2 has less aberration than B1, as, well, 0 is less than 1. Profound statement. But that's roughly the idea, is that if I have if I want to include 2 block factors in my design, I'm going to confound 3 different interaction effects or main effects, but ideally not a main effect. So then the question is, well, which one should I confound? Should be confounded? And we use this concept of minimal aberration to choose which one should be confounded. And you'll have some chances to work on this yourself in the upcoming assignment. So hopefully that helps explain this. Now, again, mathematically, there's a lot of stuff going on here. But we can kind of intuitively work our way through this and say that what we're really saying is we have to lose 3 terms, or we're going to lose 3 columns in our design. We want to lose 3 columns that are as high order as possible. Now, if I try to get rid of a third, the 3-way column, I end up losing a main effect, and that's bad. But if I just try to delete all of I can instead delete all of the 2-way interactions and keep all of my main effects. So in this case, if we go back to that original hypothetical example, I can still test all of the main effects for my 3 blood pressure drugs, blocked by old versus young, blocked by, say, male versus female. And I still have a degree of freedom to test the 3-way interaction term if I really want to. I get it there anyway, so might as well do it. We haven't lost that one yet. All right, so I think that's a lot for today. I never actually did the R coding example. So what we'll do next is we're going to jump into fractional factorial designs, and then we're going to go into blocking, and with fractional factorial designs, de-aliasing of designs, follow-up experiments. There's a lot of stuff to do. So we'll go through all of that maybe in 1 or 2 lectures, and then I will include some data examples for our 2 to the k factorial designs, because before you know it, we're going to get to 3 to the k designs, and then things really start to get fun. So I will see you in the next lecture for all of that.